equal. Oh no! I still don't get the answer. Why this question is so hard? Yes, we know that the divergent theorem, often known as Gauss theorem, is a theorem in vector calculus that connects the flow of a vector field through a closed surface to the free divergence in the volume contained. The volume integral across all sources and sinks is equal to the net flow through the volume boundary. But I still don't know how to do the question.
Did you encounter with some problem? Let us help you.
So the question is, use the divergence theorem to evaluate the flux internal in spherical coordinates. Calculate surface integral where vector field is given 3xy squared, x exponent z, and z cubed. S is the surface of the solid bounded by the cylinder, y squared plus z squared equal to 25, and the plane x equal to 94 and x equal to 3. So we know that surface integral can be expressed in divergence theorem, which is triple integral of region V of divergent vector field F and differential V, and also can be expressed in triple integral of V and partial differential of vector field F dV. So from here, we need to do the partial differential first, which is partial of P with respect of x is equal to 3y squared, partial of Q with respect to y equal to 0, and partial of R with respect to z equal to 3z squared. So from the equations, we know that y squared plus z squared equal to 25, and not that y squared plus z squared also equal to r squared. So we substitute y squared plus z squared into r squared, and the equation will be r squared equal to 25, and we will get r equal to plus minus 5. And the equation state that x equal to 94 and x equal to 3. So from that, we need to sketch to find the limit of region. So we get the circle on YZ plane, which is with radius of 5, and the length of the cylinder is 3 till -4 on x-axis. So the limits of x is -4 to 3, the limits of r is 0 to 5, and the limits of theta is 0 to 2 pi. So now we have all the information. So we proceed to the calculation, which we use divergence theorem, where triple integral over the region V, the partial differential vector field F differential V. So we substitute the partial differential vector field F to 3y squared plus 3z squared. So this dv, we will change it to the spherical coordinate, where r dx dr d theta. So we will obtain triple integral over the region V, 3y squared plus z squared r dx dr d theta. As I mentioned before, y squared plus z squared is equal to r squared, so we need to substitute that here, and we will obtain 3r squared r dx dr theta d theta, and we multiply dr, so we get 3r squared. So since we know the limit already from the previous, so we will change it to the, for d theta we change it 0 to 2 pi, r 0 to 5, and x is -4 to 3. So we will get the equation is 3r squared dx dr d theta. So we integrate dx first, where we will obtain 3r squared x 3 to -4. So we substitute x to 3 and to -4, and we will obtain 21r cubed dr d theta. So now we integral with r, where we will obtain 21r power of 4 divided by 4, and the limit is 5 to 0. So we substitute r to the limits, where 5 and 0, and we will obtain 21 multiplied with 5 power of 4 divided by 4, and we will get 1325 over 4 d theta. And now we integrate theta, where we will get 1325 over 4 theta and the limit is 2 pi to 0, 0 to 2 pi. And we substitute theta with 2 pi and 0, and we will get 13125 over 2 pi, or it can be 6562.5 pi.
For your information, Aiza, we can also solve our question regarding divergence theorem by using MATLAB software. And as you can see here, the MATLAB simulation result will give us the same value as we calculated. And I can also show you how to solve our question that we have discussed by using MATLAB simulation with just a simple command. So let's go. Okay, this is MATLAB software, and I will show you how to solve our divergence theorem question by using simple coding in this MATLAB to evaluate a flux integral in cylindrical coordinates. So firstly, we need to define our function of cylindrical coordinate, which is f x r theta equals to 3r cube. So the command will be f equals to as we can see, we already defined our function, and then we can enter. Okay, here is our function. Next, we need to define the limit of our integration. However, when we do manual calculation, the notation of our integration is at x first, r second, and the theta is third. But in MATLAB simulation, we define the limit of integration at theta first. So here is our command. I will show you. The command will be integral 3, because we do triple integration. In the bracket, f is our function. The limit of theta is from 0 to 2 pi. So theta is equal to 0 and theta is equals to 2 pi. Next, for the limit of radius is from 0 to 5. So r is equals to 0 and r is equals to 5. Lastly, the limit of x is from -4 to 3. So limit of x is -4 and 3. Close bracket, enter. So this is our answer that we get from simulation. As the result, the internal flux in cylindrical coordinate using MATLAB simulation is approximately the same as we calculate.
So right now, let me help you to sketch the graph by using the GeoGebra app. From the question, it says the solid with the equation of y squared plus z squared is equal to 25. So this equation is actually an equation for cylinder. By putting this equation at GeoGebra apps, it will generate this solid. Next, it said that the solid is bounded with plane x equal to 3 and x equal to -4. So these two planes, it will be vertical towards the x-axis and parallel towards y-axis. So by putting these two planes into the GeoGebra apps, so this region will be displayed. So here is for plane x equal to 3, and here is for the plane x equal to -4. So lastly, we need to determine the region R. The region R is very important for us to determine the type of region we are going to use for double integral, whether we're going to use a type 1 region or type 2 region. So this region can be obtained from the equation y squared plus z squared is equal to 25. So this equation will create a circle at y and z axis. So how we know the radius? By square root the 25. So we square root the 25, we'll get 5. So that it will be a radius of 5 on the positive side and -5 on the left side. So here is the graph that have been obtained from the GeoGebra apps for the region R at y to z axis.
So are you clear now, Aiza?